Perfect. So we're going to continue with the next lecture, a fourth, I think the fourth is it, the fifth lecture in our series on training neural networks. And today we're going to primarily discuss incremental update algorithms. Now, in the last lecture, I sort of rushed through the last couple of topics. I had the luxury of doing that because we're going to be revisiting those topics in this lecture. So here's a quick recap of what we've covered so far. We've seen that neural networks are universal approximators. We've seen we must train them to approximate any function, and that they are trained to minimize a total error on a training set. And we do this through empirical risk minimization. We also saw that we use variance of gradient descent to do so, and gradients are computed through backpropagation. We also saw that vanilla gradient descent may be too slow or unstable, so better convergence can be obtained through a variety of means. Topics that we had on the slides, but I didn't cover in the lecture, was second order methods that normalize the variation across dimensions. We saw adaptive or decaying learning rates can improve convergence, and methods like rprop that decouple the dimensions can improve convergence. Momentum methods, which emphasize directions of steady improvement and de-emphasize unstable directions, also improve convergence. We saw these. So let's move on. Here are the topics we'll cover in the remaining lectures in this series. Today we're going to discuss incremental updates, revisit trend algorithms in this context, and then later in the next class we will discuss generalization and various tricks of the trade for training better models. So our first topic is incremental updates. Now recall our poll for you guys. For those of you who can't see the poll, this is the first question in the poll.
I love the confused look on everyone's faces right now.
Okay. So, yeah. The answer is no. Anyway, this is just to warn you kids, those of you who are here up and early, that there will be a quiz question on the lecture slides. Specifically, I'm going to be asking you how many hidden slides there are in the lecture, in today's lecture. If you're watching the lecture, then you will know the topics that were covered. Then if you go through the slides on the course website, you will know which ones were not covered. It'll take you maybe a couple of minutes to identify the hidden slides and count them. If you're not watching the lecture, and I'm speaking, if you're not paying attention through the entire lecture because you need to know what was covered in class to answer that question, you won't get it right. Anyway, so here's our training formulation. We want to train our network to approximate a function, for example, the one shown by this curve. And this means we want to learn the network parameters such that for any x, the output will be as close as possible to this curve, f of x. Now, only when we learn the network, we won't know the entire function that we're trying to learn. Instead, we only know the input-output relationships at a small finite number of points shown here by these vertical lines. This is the input. Was there a question? No. Okay. So for each input, we would know the corresponding output for a certain number of these inputs. And we are going to train the network to learn to compute the correct output at these points. And we hope that in that process, we will sort of learn the network, the function everywhere else, even though we haven't actually seen the points. And to learn this input-output relationship, we're going to use gradient descent. We'll initialize our network, which gives us an initial function, maybe like this red curve over here. And then the gradient descent update adjusts the network parameters to try to reduce the average error over all of the training points. So you will be considering the entire lot of training points. You have the average error over all of them, and then when you try to adjust the network parameters to minimize the average error, because you're considering all these points, you will be trying to adjust the error at every one of these training points. So you would push up, you find that the network is under predicting the function at these points and over here. So the network parameters would be adjusted to increase the value of the function at these points. You find that the function is over predicting the target function at these at these locations. So your update is going to try to push the function down at these points. And this update is going to give us a new function shown by the red curve, which may still be off. So at the next iteration, again, you would minimize the average error over all of the points. And so you would try to push the function up here and then shrink it and reduce it down here. And that would give you a new point. And we're going to keep iterating this process till trying to correct the error at every training point in each iteration. Now, this process where we consider the total error over all training points and update parameters to try to minimize this total error is what is called a batch update. You update the parameters after considering the total error over the entire training data. Now, this is the actual objective because the loss that we defined is the training loss. It is the loss over the entire training data. And when we try to minimize the training loss, you will be trying to minimize the total error over all of the training points. That is, in fact, our actual physical objective. The problem is that we have to simultaneously try to adjust the function at every one of these training points, which means that before each update step, we must process the entire training data to find out the mistakes that are being made at every single one of these points. And the number of training data could be in the millions or even the billions. So this is a large computational load. Now, an alternate approach is to adjust there's a poll. So for those of you who can't see the poll, the second question over here, slide 28, this is the poll. Okay, to answer the question, all of these options were right. The loss function is not the same as the loss is the empirical risk, remember? So the loss function we try to minimize is the average divergence over the entire training data, which means if you want to minimize the actual loss function, you must minimize over the entire training data. It requires batch updates. So batch updates do minimize the total loss over the entire training data. And so they optimize the actual loss function. The first three choices were the same choice. All three must be right. And of course, because you're processing the entire training data, batch updates require processing the entire training data before each update. Questions, anyone? Any questions? Nothing in chat? Okay. So now, so you can think of trying to adjust the function as, say, let's say you have a very stiff handkerchief, and then you have some shape that you want to make the handkerchief into. So then what you can do is, stick 100 fingers, sticky fingers on the handkerchief, and try to pull the whole sheet up so that it models the shape that you want. That's really what you're doing when you're performing batch updates. On the other hand, there's a different way of doing it. If you were asked to sort of shape a handkerchief, you're not going to be able to sprout 100 fingers all at once. So what you would do is to pick it up and keep pulling it up at individual locations in the handkerchief, pulling it up in one place, pushing it down in the other, and so slowly sort of molding it into the shape that you want. So you're not molding the entire surface all at once. You're doing it one point at a time. But if you do it carefully enough, eventually, anybody who's done any kind of clay modeling or any kind of modeling, you know that you will get the required shape. So we can computationalize this process. This is the alternative approach where you adjust the function one training point at a time. So instead of trying to adjust the function at all of these points, let's say you pick up just this one training instance, you find that at this training instance, your function is under predicting the target function, you push it up. Then you pick up another training instance, you find that over here, the function is also under predicting the target function. So you adjust the parameters to push this up. And then you go to another point. Here it's over predicting it. So you're going to adjust the target parameters to push the function down over here. And keep repeating this process. At each input, you're going to keep the adjustment small. And eventually, when you've processed all the training inputs, we would have adjusted the function at every one of these training points. And now, instead of making just a single update after processing all of the training points, what would have happened is that instead of one large update from all of the training points, you'd have made many small updates. But although each of the individual updates may be very small, because you made so many of them, cumulatively, you may actually end up with a greater adjustment than if you performed a batch update where you considered all of the points all at once. So, questions? Anyone?
There was a question about the last option of the poll, and it says, don't we in practice run a batch through the network and then compute and propagate the loss of that batch?
So when I'm speaking of a batch update, you're really saying the loss. So how do you understand the loss? What is the loss? So whoever asked this question, can you answer me? How did we define the loss?
Isn't it the error?
The error over what?
I assume since we're asking, it's going to be error over the training set.
The error over the entire training set, right?
Mm-hmm.
So that's what you're trying to minimize. The fact that you're not actually implementing things in that manner is what we're discussing today. But what you really want to implement is to minimize the error over the entire training set. Right?
Okay.
Right? Which means you want to minimize the total average error or total error over all of those lines, not just at one point, or not just at any subset of points. Make sense?
Okay.
Yeah. So what we are doing here is that we find that when you want to make adjustments in a gradient descent framework, mind you, if you had a closed form solution, probably just making one pass over the data and then optimizing a function and getting a solution. I mean, not probably. In reality, the optimal thing would be to just go over the entire data, get a closed form solution over the entire training data, and then just update the parameters once, because it's a closed form solution. In gradient descent, because of the incremental nature of the algorithm, going over the entire training data for each minor update is going to be horrendously expensive. And so we begin doing this online process where you can pick a point, adjust it there, pick another point, adjust it there, and so on. And the hope is that when you're done with all of the training data, having made one pass over it, instead of just one update, you're going to get as many updates as there are training instances. And of course, remember the handkerchief analogy? If you're sort of poking and pushing and modeling your handkerchief into a shape, you can't be pulling it by large amounts at each point. You're going to make small adjustments. So although the individual adjustments are going to be small, cumulatively over the entire set, eventually you're going to get an adjustment that might just be larger than what you would get if you did a proper batch update, which considered the entire collection of training data.
So there's one more question.
Yeah.
How do we make sure that the effect of the adjustment at one training point is local?
Okay, so we're going to go over that in the next few slides, okay? So it won't be local. When you make an adjustment at one point, it's going to change the entire function. This is guaranteed. But it's going to be change it more at that one point than at other locations. So anyway, just I have some pseudocode for this. I'm going to gloss over it, but the only difference here is that within each, okay, here's what we're doing. You're going to initialize all your parameters. You iterate. Within each iteration, you go through all of the training data. And for each training instance, you compute the derivatives for every parameter, and then immediately adjust the derivatives, the parameter using the derivatives that you just got after each instance. So these iterations can take multiple passes over the training data. It's not that you're going to do just one pass. You will be making multiple passes over the entire training data. That's what we call an epoch. But within each epoch, if you have T training samples, you're going to make an update after each sample. So you're going to have T updates of parameters within each epoch. So here, this outer loop is iterating over epochs. This is one epoch, which is just looping over the instances. This is one update. Now, there's a problem with doing things in this manner. Let's consider this extreme example. Let's say I have a function whose architecture constrains it to be some kind of a curve of this kind. I'm trying to adjust this curve to best explain these 8 training instances. And now in all 8 training instances, the training points have the blue line is the target function. And I'm trying to adjust it. So suppose my training instances were organized in this manner, 4 to the extreme left, 4 to the extreme right. And then I loop over these training instances by going left to right sequentially. What will happen? Initially, I'm going to adjust them for the 4 training instances to the left, which means I'm going to push the function down till it's given me 0 error over here. But in the process, it's got sort of raised the function up out here. Then I'm going to move right and begin making adjustments for these guys. And when I do that, it's going to push the function back down over here, and voila, it's gone back and undone what I did on the left-hand side. So then I have to go back to the left and then push it down. It's just going to keep bouncing back and forth. Every time I process the instances from the left, those got fixed, but then I made mistakes to the right. And then when I process things to the right, those got fixed and I made errors to the left. So why is this happening? Can anybody tell me? Answers anyone? Why is this happening in this particular example?
We are always using the same sequence of input, so we might need to randomize that.
Yeah, if you use the same sequence of inputs, you're going to be correcting for these guys, make an error here, then you correct for these guys, and then you undo what you did. So what you really want to do is to go through them randomly to get more convergent behavior. So you would randomly pick something over here, push the function down here, then just randomly choose something, and maybe something over there, you adjust the function there, and keep doing this. And so long as you keep randomly selecting our training instances, you will be pushing the things sometimes to the left, sometimes to the right, and eventually you're going to get the right kind of behavior from the function that you're constructing. So it's important for this process to work. It's important for you to randomly select the training instances, which is where the notion of stochasticity comes in. you're stochastically selecting your training instances. And so this entire process is called stochastic gradient descent. Stochastic because we randomly select the training instances, and gradient descent because after each selection, we adjust the parameters with the gradient of the divergence for that one instance. So here is the entire pseudocode for stochastic gradient descent updates again. It's the same pseudocode as I had before, but I added one extra line. Within each epoch, before I loop through the data, I have randomly permuted the training data. So randomly permuted the training data is essentially the same as randomly sampling my training instances without replacement for each update. And so this is a stochastic update method, specifically stochastic gradient descent. And so the story so far, in any gradient descent optimization problem, presenting training instances incrementally can be more effective than presenting them all at once, but only so long as the training instances are provided in random order. And this is not specific to neural networks. This is for any kind of function that you're trying to learn. So obviously it also holds for neural networks, which are just functions, as we saw. Now, so the question is going to be, why does this process of incremental updates work and under what conditions? Why should I believe that just picking my handkerchief a little here, pushing it a little there, and doing it one spot at a time is going to give me an overall acceptable model estimate? And under what conditions is this going to be worse than just grabbing the handkerchief, at all the function at all training points and adjusting it? And under what conditions is it going to be better, right? So let's look at the why it works, and I'll give you a very simplistic explanation to begin with. Now, remember the actual loss that we computed? The actual loss that we computed was, let's go back to my empty slide. The actual loss that we had, how did we define it? Anybody remember? What was the loss? Someone tell me. Anyone on chat? I'm going to wait.
And no answers on chat right now.
So I'll wait for you guys. If you don't answer me, the class is done.
The divergence between the the desired output and the actual output, right?
Which desired and which actual output?
So the desired output would be the actual output of our neural network, and the actual the real output would be the label, right?
Right, but is it going to be just for one instance? Is this how we define the loss?
So we still need to do an average before the whole thing because we're coming in the batches, right?
Wait, we are coming in batches, or what do you mean by?
So
what do you
no,
mean
we have a whole training data set, so we need to do an average for.
We need to do this over the entire training data, right? This is the loss part. This is the loss function that we want to minimize. Now, consider this guy. Is this a function of the weights? Yes or no?
Yeah.
Right. And is it going to be the same for every single training instance? This function?
No.
No, right? So what we are doing is we're averaging many functions. Now, when I take the derivative with respect to, okay, I should really be writing this in vector form, then what will this derivative be? Remember? This is once again, is this going to be an average, or is this going to be just one term? Let me help you, right? The linearity says it's the average of the derivatives of the divergences for the individual instances. You remember this? Anyone?
Yeah.
Okay.
Yeah.
Okay. And is this guy going to be the same for every training instance?
No.
No, they're going to be different, right? Okay. So here's what happens. This loss function is the average of many different divergence functions. These are the parameters. This is the loss. And so if I have a current estimate, which is say here, and then I look at the derivatives of the divergences for the individual training instances, each of them is going to be pointing in a different direction. The overall divergence that we are going to use for the actual batch update, right? So what was the actual batch update again, guys?
Using all the data at once.
Using all the data at once. That's what we really want to do, right? And so when I compute the overall divergence using the all batch or the actual batch loss, that's going to be this overall divergence. How does this red arrow relate to all of these blue arrows? Someone?
Vector sum.
Vector sum?
The mean.
That would be the
mean.
average.
Isn't the
going to
average?
be the average, right? It's going to be the average. So this is the direction that the average divergence is going to be in. Now, suppose I give you this extreme example where I have a collection of training data, and for some reason, all of the training data are identical, right? So in this case, are the derivatives of the divergences for all of these training instances going to be pointing in different directions?
No.
Okay, so what will the average be like?
Like the same as the individual one.
It will be the same as the individual ones. Now tell me this, in computational terms, if I first process the entire training data and then compute the average divergence, that's on one hand. And on the other hand, I just compute the divergence for a single instance. Are these two going to be different?
No.
They're going to be the same, right? And so in this situation, when everything is identical, the average divergence is going to be the same as the individual divergences. In this case, is there any advantage to actually performing a batch update over stochastic gradient?
No.
Not really.
No.
Okay, so is there any disadvantage?
It could take longer to go through all the data.
You're going to, how, can you give me a number on how much longer?
O of n.
All of n, O of n, right? Because what happens is that when I'm performing a batch gradient, I will have processed the entire training data and made one teeny update. And the same amount of time, I would have made 10 updates using stochastic gradient. Which is better?
10 updates.
Definitely stochastic.
Obviously the one to the right, right? Obviously the one to the right. Now, suppose instead of being all identical, the things were all clumped together. They're not identical, but they're all very close. Is the situation going to be different?
No.
It's going to be more or less the same, right? As the data get increasingly diverse, that's when the benefits of incremental updates are going to begin to decrease. They don't entirely vanish, but that's when they actually begin to get decrease. And when is the situation, what is the worst case situation? When the data are actually spread over the entire space. Make sense to you?
So do we measure the variance of the data? Should we measure the variance of the data before?
We could, but we
deciding?
don't do it. We just work off, this is the intuition behind what we are doing. There's a lot more to it, okay? But obviously, the less varied the data are, the more you're going to gain from stochastic gradients, right? Now, so we saw why it works, but then when does it work? while the previous example provides a good intuition, it's not the complete story. We need to have additional considerations. Now, what happens is that you don't actually get a perfect fit for the entire training data. So think of trying to find a linear regression for all of these data points. Then the actual linear regression is going to be this line, which kind of fits all of them, correct? But then if I were to be looking at stochastic gradients and say looking at one instance at a time, so I've got all of these guys, my points, and I have my line here, that's my ideal line, right? Even if I start with the ideal line, when I'm going through stochastic gradients, let's say consider this one initially, what will happen to the line? This line is wrong for the speller, right? I can fix the line by making it go through this point. But now this is not the line that I really want. Now at the next instant, I might just randomly go ahead and pick this data point. And now this line is going to be wrong for this guy. So now the adjustment is going to try to push that line through this point, right? And as you keep going through the data, you're going to have this never-ending non-convergent updates. Correct? So how would you fix that? Let me say, how would you fix that?
We can have a small threshold for the as the ending criteria, I guess.
Well, the point is, yeah, not really. So here is the point. So long as you have a fixed learning rate, a fixed step size, this thing is going to keep oscillating. The latest data point is just going to drag the estimate towards itself. So imagine, again, going back to this handkerchief thing problem, right? Visualization. How would you deal with it?
I think you could consider a couple of points.
We could, but if I'm considering only one point at a time, what you would normally do is initially you'd make lots of big changes, but then as you begin getting the shape, you're going to make smaller and smaller adjustments at each point, right?
So then do we have to decrease the learning rate?
You have to decrease the learning rate with iterations. You must shrink the learning rate with iterations to prevent this oscillation. That way, eventually the correction for individual instances with the eventual minuscule learning rates is not going to modify the function. So here is the modified pseudocode. This is the same one as before, but now there are two things happening. Of course, I'm randomly permuting the training data for each epoch. And then I keep track of the iteration where each update is now an iteration, right? And the learning rate is going to keep shrinking with iterations. Now, so assuming I have done this, right? Let's go back to this problem, not to this problem. Can you think of any conditions? We've agreed that the learning rates must shrink with iterations. Can you think of any conditions that would apply for this whole process? Anyone? Can I just arbitrarily shrink the learning rates?
Would we have to shrink the learning rate based on total error or the error that we get? So once we've reached a certain amount of error, we decrease it, and then once we reach the next threshold of error, decrease it again? Okay,
so you're getting to the point. Let's say this is the location of my optimal estimate, right? This is my W opt. And then let's say this is my W0, right? My initial estimate. And now your loss function, the way we've defined the loss function, it has bounded derivatives with respect to the parameters. So let's say that I have dl over dw. The derivative is always bounded. It's less than some constant, right? So what does this tell me about the individual step size? What is the largest step size I can get if I'm using some learning rate eta? Anyone?
Someone on the chat says C.
Should be C.
Is it going to be just C? It's going to be eta C, right?
Oh, yeah.
Right, okay. Now tell me this. I have eta JC. I must get from this point to this point. What can you tell me about eta?
Eta changes over time.
Yes, perfect. And can you tell me something about the properties, what's the condition it must satisfy? So look at this. Each step is, what is the upper limit? It's going to be eta 0C, right? Then the next one is going to be eta 1C. The next one, this is the upper limit. This is going to be eta 2C. So what is the total change over all of my iterations? It's going to be bounded by, it's going to be eta 1C plus eta 2C, is less than, right? Because C is an upper bound, plus eta 3C and so on, which is summation I eta I times C. Make sense? So,
Yes.
okay.
I have a quick question.
Yeah.
Wait, so how do we get C? Where does that come from?
C is, you have a loss function, right? So your loss function has an upper bound on its slope.
Oh, okay.
Correct?
Yeah.
Okay. So now, if this distance is D, what can you tell me about the learning rates?
I don't know. It should be smaller than D.
Is it? No.
The sum of them is D over C.
Exactly. I want summation eta I C to be at least equal to, because I'm allowed to stop, right? This has got to be greater than or equal to D, right? So in other words, what is the worst case for D? It's infinity, right? Your initial estimate can be terribly bad. You can be infinitely far off. So now what can you tell me about the property of this guy? What must this satisfy?
I don't know. It should be at least equal to D.
No, so right. We've just said that summation I eta I should be greater than or equal to D over C, correct?
Oh, yeah.
So if D is infinite, meaning if your initial estimate is infinitely bad,
yeah,
then what is the condition on this guy?
C must go to infinity.
Not C. C is your upper bound on the loss. That's a property of the loss. This doesn't change. The only thing you have,
Etas go to infinity.
Yeah.
not the etas, but the summation of etas must go to infinity.
Yeah.
Right? But does that mean that the etas can just blow up? It doesn't, right?
Cause problems.
Because of the other problems that we just saw, correct?
Mhm.
So nevertheless, you want the etas to be shrinking. You want the etas to shrink over iterations. At the same time, you want them to sum to infinity. So the actual property that you get is that you want the sum of the squares of the etas to be bounded, some constant, let me call this A. At the same time, the sum of the etas to be infinity. That makes sense? This guarantees that the etas shrink. This guarantees that you can get to the solution from anywhere. Questions, anybody?
There's a question on chat asking how could loss be infinite?
How could?
Loss be infinite.
The loss is not infinite. What was this D that we were talking about? The D was your distance, right? You have an initial estimate, you have the optimal value, and D was the distance between your initial estimate and the optimal value. That can be arbitrary. So infinite is the worst case. Did that answer your question?
Wait, how exactly can the distance between the weights be arbitrarily like large?
So let's say that your
Calculate some
optimal.
bounds.
So suppose you have an optimal estimate of W is 0, and you just initialized it at 10 raised to minus 250, or 10 raised to minus of 10 raised to 250. Nobody's stopping you from doing that, right? So your initial estimate is off the charts. Whenever you come up with these with this kind of logic, you're always looking for the worst case. So we're not speaking of the value of the loss function. We are speaking of how far away you started off in the first place.
Right, see.
Make sense, right? So you need these two properties. You need this. Yeah.
Question for that last property.
Yeah.
So is it the fact that eta is between 0 and 1?
No, we have not put any conditions on eta, right?
So, okay, so now I'm lost. How could the square of something be bounded when the normal can go up to infinity?
Can you give me a series of this kind?
I'm sorry?
Can you give me a series of this kind? I'm rolling this back to you. I'm asking you for a sequence. Remember, you have eta 0, eta 1, eta 2, eta 8, right? So I want a sequence of etas where the sum is infinity, but the sum of the squares is not.
I'll need to go to pen and paper.
Harmonic series, right? Eta I equals 1 over k. Or eta k equals 1 over k. What is the sum of this one? That's
That'll
infinite.
be infinite.
Exactly.
Yeah.
So there, I've already given you an eta that satisfies this condition. 1 over k squared is guaranteed finite, right?
Okay.
So this is in fact, the fastest converging series that satisfies both requirements is eta k is proportional to 1 over k. Now, of course, this doesn't have to sum to infinity. If this is really bounded by how far away you start off with. But then considering that you could be wandering around chaotically, having that sum be as large as possible gives you the maximum guarantee that you will get to the optimum. At the same time, you must converge. So and if these properties are satisfied, then SGD will converge to the optimal solution for convex losses. For non-convex losses, it's going to converge to a local minimum. Questions?
We had a question about stochastic gradient descent, and a student asks, will applying Nesterov's accelerated gradient make SGD harder to converge?
We are going to get to that later in today's lecture. I'm being very slow, so let me try to speed up. But then here is a little example where we apply SGD to k-means. That's a good question, and so we'll get to that, right? Now here, this was batch updates to learn k-means estimates. This was SGD. And you can see and because these are iterative algorithms where you initialize, these little bars give you the variation across different runs of the algorithm. The line itself is just the average convergence. And you can see that batch updates really converge. SGD converges much faster. Where batch updates take 100 seconds, SGD converged in 1 second. So that is good. But then the actual final loss that you got with SGD was terrible, as opposed to batch updates, which were really good, right? So also, if you look at the variation across runs, the variation across runs is tremendous for SGD, but it's really very small for batch updates. Let's try to understand these results, right? Yeah, here's a poll. For those of you who cannot see this, this is poll number 3, slide 66. All right, let's stop this. Yeah, all of them are right. Right, we've just
Wait,
Spencer. Yeah. Questions?
the last one isn't right.
The convergence to the global optimum can only be guaranteed if the step sizes shrink across iterations but sum to infinity in the limit. That's basically what we
SGE
get.
doesn't always converge to global optimal.
So can only be guaranteed. It doesn't mean that it is going to be guaranteed, right? We are saying that for some kinds of functions, we're speaking of a possibility. So
speaking about that, are we still working on the convex loss function case, or are we?
So we are speaking of can only. The can be guaranteed is only for convex functions. If it's non-convex, bets are off. But still, you still want these properties to be satisfied for to maximize the likelihood that you're going to get to somewhere to a decent optimum. There's more to it on the slides, hidden slides. Okay, so let's continue. Now, remember what we did when we were speaking of modeling a function. What we really wanted to do was to minimize the expected divergence. What we minimized instead was the loss, which is the average divergence over all training instances. And we worked this out in the last class that if you take the expectation of the loss, the expectation of the loss is actually the expectation of the divergence itself. So the loss was an unbiased estimate of the actual objective that we would like to minimize. And so the empirical risk is an unbiased estimate of the expected divergence, although there's no guarantee that minimizing it will minimize the expected divergence. We saw this in the last class. There is a second result as well over here that is kind of interesting. So I have loss of W is 1 over n, number of training instances, summation I, the divergence of f of xi, and the desired output of xi. So let's say these xi's are independently drawn. Then what can you tell me about the variance of the loss? The variance of the loss because of this multiplier is going to be 1 over n squared times the variance of the summation of the divergences for the individual instances. Which, now because these are all independently drawn, I can write this as 1 over n squared. When you have a bunch of independently drawn random variables, the variance of their sum is the sum of their variances. And so I can write this as I variance of the divergence of xi, right? F of xi di. Everybody see what's happening here? Anyone who has issues with this? Let me know, because I'm just going to write I'm going to keep writing, right? So this is what we had. And how many of these terms do we have? So what is this going to end up becoming? Anyone? What does this become? Waiting, guys.
So it's 1 over n times the variance of the divergence.
Exactly. It's 1 over n times the variance of the divergence. And what is n? N is the size of the batch, the number of training instances, right? And so the variance of the empirical risk is 1 over n times the variance of the divergence itself. It's proportional to 1 over n. The larger this variance, the greater the likelihood that the estimate that you will get is going to be significantly different from the actual estimate you really want. Remember, the estimate you want must minimize this term to the right, but you are minimizing this loss. And the greater the variance of the loss, the greater the likelihood that the estimates you get from these two guys are going to be very different. So now let's look at, we'll go over this in a little more detail, but let's consider SGD. SGD, so you can see over here immediately why increasing the training size is going to be a good thing, right? As you increase the training size, this 1 over n keeps getting smaller and smaller and smaller, and eventually the variance is going to become so small that you're going to get the correct answer. So because there will be no variance, which means that if you minimize the loss, you will actually be minimizing this guy. That makes sense to everyone? If it didn't, let's blow ahead, okay? Now, at each iteration, SGD focuses on the divergence of just one single sample, right? So what is so SGD, it doesn't consider the average. What SGD considers is within each iteration, it's just focusing on, this is LSGD, of a single instance. What is the expected value of the SGD loss? Anyone? If I take an expectation, what's this going to be?
The expected divergence.
This is just going to be the expected divergence, which is basically exactly what you want. So this is an unbiased estimator. It's going to be, because even if you're considering only one sample, the expectation of your loss is the expectation of the divergence. What about the variance? What's it going to be?
Zero, right?
Zero? No, this is, remember, it's
just one.
It's just going to be the variance of the divergence itself, right? For a single instance, it's a randomly drawn sample. And so if this doesn't make sense, we'll actually we'll see this pictorially. But the sample divergence is an unbiased estimate of the expected error. But the variance of the sample divergence is the variance of the divergence itself, which is n times the variance of the empirical averaged minimized by batch updates, which is why SGD is going to have a lot more oscillation in your estimates. Now, this may not make a lot of sense, but let's try to do this with pictures. So let's say I'm trying to model this blue function. I've got my current estimate of the network gives me this red function. So I want to find the W that minimizes this area, remember? But I cannot compute the area because I don't have G. So I'm going to take a bunch of training samples and I'm going to minimize the average length of these lines. So the sample average is going to minimize the estimate, which was supposed to minimize this area, is now going to minimize the total length of these lines over here. Now, if I got these as my training samples, then you will sort of realize that I have to bring the function down here, I have to bring the function down here, I have to bring the function down here, I have to push it up here, I have to push it up here, I have to push it up here, all is good, right? But then your training samples are random samples. So instead of these training samples, let's say I got a different situation where I still got only 6 training samples, but now these guys were my training samples. What do these training samples tell me? If I consider these training samples as opposed to these guys, am I going to do the same thing to the function everywhere? Anyone?
You're going to make the loss worse.
So what happens is over here, you realize that there were some locations where the function had to be pushed up. If these were my training samples, it seems to me that I'm always over predicting the function. I should be pushing it down, right? Because all of the training samples only happen in the blue regions. You have no training samples in the red regions. Make sense? So on the other hand, if I got training samples like these, I still have 6 training samples. The dominant property is to try to push up the function. You're going to push it up everywhere because all of the training samples are now in the red region. So although in each case, you had the same number of training samples, the conclusions you arrived at were different for the 3 cases. Does that make sense? Anyone?
Yes.
Okay, so how would you solve this?
Ensuring that we distribute the samples in such a way that the variance is explained.
Well, the variance of what?
I mean, for example, if we have 6 samples whereby three of them require pushing down and 3 of them require pushing up. So if we ensure that we, sample those actions equally, then we can maintain the average.
The point is you don't know that, right? You're just drawing random samples. If you knew your function so that you could draw your samples correctly, then you know the function.
Okay.
Right? The solution is to get lots and lots of samples. That way, when you have if you have a lot of training samples, then the dependence on the precise location of the samples gets greatly reduced. So that's what we mean by saying that the variance of your estimate of the weights, your variance of the estimate of the loss, and consequently the variance of your estimate of the optimal solution is going to go down as you increase the number of training samples. Did that make sense to you guys now, the formula? Questions, anybody?
I was wondering how this would just affect stochastic gradient descent in case, I mean, if you just have 6 samples.
If you have 6 samples, okay.
I mean, with the normal batch gradient descent.
Let's go back here. So SGD is going to pick only 1 sample, right? And so that's exactly our issue. So if that 1 sample fell at this location, you're going to assume, oh, everything is fine. The world is just fine. If that 1 sample fell here, you're going to think your network is grossly underestimating the function. It's got to be pushed up. If the sample fell here, you're going to assume that the network is grossly overestimating the function. It must be pushed down. And so, which is why we saw this behavior over here, right? That in SGD, depending on the location of the sample that you drew, you're going to get this wild variations in what you think you must do to the function.
Mm-hmm.
Right? Which is why you get this really bad variance behavior. And so SGD uses the gradient from only 1 sample at a time and is consequently high variance, but also provides significantly quicker updates than batch, right? So we have, because you're updating more frequently, you'll converge faster, but then you're going to have high variance. You're more likely to end up at a crappy estimate of W, particularly if your loss function is not nice and clean. That makes sense to everyone? So how would you suggest we fix this? We'd like to get an intermediate where we get the advantage of quicker updates, but we don't suffer from the same variance. What can you do?
Could you change the batch size?
You can change the batch size. You can have mini batches. You don't use the entire training data, but then you adjust the function at a small, randomly chosen set of points. As in the case of SGD, you're going to keep the adjustment small. But if you have sufficiently, if the process by which you're choosing this small set is careful enough, then these random samples are going to be distributed across the training data. So in the first set, you're going to maybe draw these guys and make adjustments, which is to say you would be pushing down the function at these 2 locations, pushing it up here. Then the next time you draw the samples, you'd be choosing a different set of points, and then you'd be adjusting the function at those points, and so, which gives you a new function, and so on. So mini batch updates. So if we sort of continue this process, drawing random subsets of training instances from our training set and updating the model at those points at each time, eventually you're going to cover the entire training set. As in SGD, you won't make very big adjustments, but you'll keep the updates within each mini batch small. And yet eventually you'd have updated the model everywhere and hopefully with better effect than either simple SGD or batch training. And again, like in the case of SGD, for this to work, you need randomness. you cannot keep going through the training data in the same order every time. You will end up with cyclic behavior. And so here's the pseudocode. I sort of gloss over it, except the fact that now you're working in batches. You're computing the average derivatives over the batch and using those to update your parameters. Right, so you have a mini batch and you still need shrinking step sizes. Now, the loss minimized in the mini batch updates in each update is going to be the average divergence over the batch. What is the expected value of this mini batch loss? Just looking at this function, you should be able to tell me. Anyone? Guys?
I guess it's the same.
Yeah, if you take the expectation, you're going to end up with the answers on the screen, right? The expectation is that if I take the expectation, I'm going to get 1 over b times the summation of the expected value of the divergence. It's also the expected divergence. So the mini batch loss is an unbiased estimate of the expected loss. What about the variance? What is
Still
it?
the same?
Is it the same?
Maybe.
Okay, go back and look at this fellow over here, right?
Variance
Is it b over n?
There is no n over here, right? Now we are working off a batch size of size d. So the variance of the mini batch loss is going to be the variance of the divergence divided by b. Remember, for the full batch, it was divided by n. In every case, you're going to be minimizing by the size of the batch that you are using. In the case of stochastic gradient, that batch size was 1. In the case of batch training, it was n. In the case of mini batches, it is b, right? So the variance for this guy is going to be, so the variance of the mini batch loss is going to be 1 over b times the variance of the SGD loss. Did that make sense to you guys? Anyone who didn't get it? Questions? Okay. Anything on chat?
No, nothing.
Okay. So tell me this. This is my batch size. Okay. How does the variance of the loss function change with batch size? What's it going to look like? Anyone?
Decreases?
It's going to decrease like so, very rapidly, right? This is where you are with SGD. This is where you would be with your full batch. And as you increase your training set, that variance is going to keep decreasing towards 0. And this is where you're going to be with mini batch. Obviously, this is way better than this guy, right? Maybe not so good as this one, but really the gap between these two is small enough that it becomes insignificant for a large enough batch size. And so the variance of the mini batch loss is 1 over b times the variance of the divergence. This will be much smaller than the variance of the sample error for stochastic gradient descent. So going back over here to the same k-means example, what you will see is this was what we got with full batch, the convergence. This is what we got with SGD. It wasn't very good, but when you use mini batches, you're getting the fast convergence of SGD. You're getting approximately the same kind of final loss that you got with the full batch. And the variance you get is comparable to what you got with the full batch, because if you had a training set of 1,000 points, the variance is 1 over 1,000. If you had your mini batches of size 100, its variance is 1 over 100, but 1 over 100 is already a really small number, right? So so in general, because the variance falls very rapidly, the variance of the loss falls very rapidly with your mini batch size. Even having a mini batch size of say 100, is going to give you a mini batch loss such that when you estimate your parameter updates from it, they're going to be pretty close to what you would be doing with a full batch. So, which is why when we train neural networks, we generally use mini batches. Now, there's this issue of how do you actually define convergence. Convergence is defined in terms of the overall training loss, not on sample or batch losses. And regardless of whether you're doing SGD or mini batches, you can't really compute this guy, because this would mean that after every update, you're going to pass your entire training data through the model and computing the average loss on the entire data, which is kind of stupid, right? So we usually come up with various kinds of heuristics to estimate the loss. When you plot your loss plots, those loss plots are not accurate. They are not telling you the true story. The true story would be the loss on the entire training data. But clearly, you're not going to be plotting that. So we use various other tricks like divergence or classification error on a held out set, or some average of the loss over the past 10 batches, or some running estimate, the various tricks that you guys have been using.
Professor, there's a question on the chat. So what happens in the long run? Would SGD loss gradually drop to the same level as the other two updates?
So for convergence, for convex functions, if your update rules satisfy the properties that you just said, yes, it should. For non-convex functions, it's really not very clear. So here, for example, for the k-means estimate, you can see that I could convert this and it's going to sort of saturate somewhere around here. Whereas these guys go somewhere else. And this is something you can quickly run your simulations and you will find this to happen every time. Right? It depends on the loss function. In general, mini batches are just going to be better than SGD, both in terms of computation, because you can vectorize mini batches much better than SGD, and in terms of the loss and in terms of the final performance. Right. So in practice, training is usually performed using mini batches, but the mini batch size is a hyperparameter to be optimized. And the convergence depends on the learning rate and all of the other things that we said still helped. So I'm going to skip over I'm going to sort of fly through the rest of it. So SGD, presenting training instances one at a time, can be more effective than full batch training, but then the learning rate must shrink sufficiently rapidly with iterations. SGD estimates will have higher variance than batch estimates. Mini batch updates operate on batches of instances at a time. So they will have lower variance than SGD. The convergence rate, if you look at the slides, it's theoretically worse than SGD in terms of actual CPU time, but because you can perform vector processing, it actually ends up being much better. So now, convergence depends on learning rate, right? As I mentioned, we need to have optimal learning rate schedules or decent learning rate schedules for the whole thing to work. And there are various tricks like things that you've been seeing, fixing the learning rate till the error plateaus, then you reduce it, or adaptive updates where the learning rate itself is determined as part of the estimation. Various things that people have tried, but the learning rates must satisfy those two properties that we mentioned earlier in any case, that the sum of the learning rates must permit you to get to the optimum solution, and they must shrink. So let's go ahead and revisit trend algorithms. Questions, anyone? Yeah, there's a poll. For those of you who cannot see the poll, there it is. This is lecture 98, slide 98, this poll. Okay, let's stop here. But so the second option is obviously wrong because mini batch descent with a batch size of 1 is the same as SGD. The other three are all right. So let's go back to trend algorithms. Now, one of the problems with both SGD, with SGD in particular, but also to some extent with mini batch, is that you have variance, which means that each mini batch is actually seeing a different loss function than every other mini batch. As a result, your estimates are going to keep bouncing around, right? Your updates are going to be bouncing around like so. And this can result in ugly convergence. And so the kind of trend algorithms like momentum that we saw, which smooth these trajectories, end up being much more important for SGD and mini batch. Now, we've already seen two of these trend algorithms. One was momentum. In momentum, what we did was, suppose we had taken a step of this kind at, say, the kth iteration. Then at what we did was we computed the gradient step, which is going to be eta times the gradient of the loss with respect to W minus. And then to this gradient step, we sort of went back and added a little bit of the previous step size, which was some beta times delta WK. And this result was what was the K plus 1th update. And this guy was what we used to update our parameters, if you remember this, right? This was the momentum method. Then we also saw, so if you were doing this with SGD, you would still be doing exactly the same thing, except this derivative over here is now going to be your SGD, the derivative of the SGD loss or the mini batch loss. And there you're going to get a lot more oscillation. And so the blue arrows over here show you the typical behavior of these mini batch losses. And you can see that, you know, although it's just an illustration, you expect it to sort of bounce around, but the momentum smoothing sort of cleans it out. Now, same thing with, skip the pseudocode. Same thing with Nesterov's method. In Nesterov's method, we did something else. In Nesterov's method, suppose you had initially made an increment, a delta. If this was delta WK, then you extended delta WK to a new point. So you got delta WK plus some beta times delta WK. Right? This is, so you sort of extended it. You computed the derivative of the loss at this point, and then you took a step size against that derivative minus eta, and this was your the actual final step ended up being this guy over here, right? So you would compute this gradient, this term, plus this term itself. So it's going to be beta times delta WK, which is this one, plus the gradient step computed at the new point, which is this guy. That gave you the new delta WK plus 1, right? So that's what we used in Nesterov's method. And once again, if you were using Nesterov's method, this derivative is going to be computed from your SGD or your mini batch loss. Now, and the problem is momentum and Nesterov's method are actually minimizing the considering the average value of the gradients. So what we said was, if your gradients were like so, then we said that you're getting a lot of oscillation in the upward up-down direction, but you're getting steady progress in the forward direction. So if you took the average is going to cancel out the up-down variation, but it's going to retain the horizontal variation. And that's what momentum was doing. The problem here, so guys, again, like every other class, I'm going to go over by 5 minutes. Please stay with me, right? So like every other, like the problem here is that, so let's say I have this situation here. And then I have another case where I have this situation. If I take the averages in these two cases, will the averages be different? Anyone? Each of these is one, the derivative computed at one of the updates. So this was a 0th estimate, the first, the second, the third, the fourth, the fifth, the sixth. Same here. So what the momentum methods were doing was trying to take the average of all of the previous derivatives to smooth out the oscillation. Are the averages going to be the same in both cases?
Yes.
Is that a good thing? Or is there something we're missing?
We see a lot of no's in the chat.
Okay, great. We are missing the fact that this guy is actually oscillating a whole lot more, right? So in this case, we want to be shrinking the up-down variation a whole lot more than in this case. Because this is really a bad thing to be doing, much worse than this guy, right? The total, so that is something Nesterov and momentum completely ignore. So for example, if you look, and how can you quantify that something bad is happening? This is a two-dimensional example. I have shown you the X and Y components of the steps in each iteration for several iterations. And you can see that the X component is always steadily positive. The Y component is swinging positive and negative, right? Now, I have two cases over here. I have this plus 2.5 minus 3 plus 2.5 minus 2 and 1.5. And then another case, I have plus 5 minus 6 plus 5 minus 4 and 3. Of the two, the second case is clearly the worst thing to be doing, right? So how can I actually quantify that this is the worst thing to be doing? By looking at the total variation. So if I just look at these steps, the total variation in the X direction is 1 plus 1 plus 2 plus 1 plus 1.5, which is 4, 5, 6.5. And I made some progress along X. The total movement in the Y direction is 2.5. Because you're speaking of movement, you ignore the sign, right? How much did you actually walk? How much energy did you expend? That's going to be 2.5 plus 3 plus 2.5, which is going to be 8, 9, 10, 11.5. And so what happens is that although we walked only 6 steps in this direction, we made a lot of progress. We walked 11.5 steps up and down and basically didn't change at all, right? So you want to consider the total variation and not just the average to decide what to do. So a lot of these, so the fancier methods will modify the usual gradient-based update. They're going to scale the updates in every component in proportion to the total movement of that component in the recent past. And this is going to change the update sizes for the individual components. So in this example, it's going to scale down the step sizes, the learning rates for the vertical component. It's going to sort of also modify the learning rate in the horizontal component, but not so much. So there are several techniques which are based on this simple principle, and you have encountered at least one of them. I'm going to be presenting two. The first is RMS prop. RMS prop is, I have some notation actually. The derivative RMS prop is applied, all of these techniques are applied individually to every weight, to every component of the parameter vector. So this term, partial W of D, is the derivative of the loss with respect to the parameter. When I say partial squared W of D, it's not the second derivative, it's the square of the derivative. And the mean square derivative is the expected value of this guy, right? This is just notation. So here's what we do in RMS prop. We keep track of the squared the square of the derivative, and we maintain an average of the square of the derivative. Now, if you look over here, if I take the average of the square of the derivative, this is going to be 2.5 squared, 6.25 plus 9 plus 6.25 plus 4 plus 2.25, right? I'm going to take, and then, so I'd add those up, and then I'd take an average, and that gives me the average, the second moment in the vertical direction. Here it's going to be 1 plus 1 plus 4 plus 1 plus 2.25. If I take the average of those guys, it's going to give me the total moment in the horizontal direction, and you will find immediately that the total moment in the vertical direction is a lot more than the total moment in the horizontal direction. Now, instead of just keeping track of all of the movements, you just maintain a running average. So you would have the expected value of the square of the derivative for each component is some gamma times the estimate for that guy in the previous iteration plus 1 minus gamma times the square of the derivative in the current iteration. So that gives me the squared movement of each of the parameters. And my learning rate is going to be normalized by the square root of this term. This epsilon is just to prevent division by 0. So this learning rate is actually going to, so when we normalize by this guy, this is the root mean squared value. What this means is that if the root mean squared value is large, it means you have a lot of variation in that direction. So that direction is probably not a good thing, not a good direction to be changing in. And so your step size is going to shrink. On the other hand, if the RMS value is really small, it means that's a good direction. You're not oscillating wildly, so you're going to take a larger step size. Now, if you observe this, RMS prop is basically very similar to R prop. If you have a constant derivative, meaning you have a function, a loss function, which has a steady slope in some direction, then this derivative is going to be the same at each step. So the RMS value is going to be the same as this guy. This ratio is going to be the value of the derivative divided by the absolute value of the derivative, because the RMS value is going to just be positive. The only thing that will remain is the sign of the derivative. So this ends up being just like R prop, where you only consider the sign of the derivative and not the value of the derivative itself. Now, so here's pseudocode for RMS prop. I'll skip that. Now, the problem with RMS prop is that it's only considering the second moment, the squared values of the derivative. So it says, is this oscillating a lot? I mean, does this have a lot of variation or does it not? But it's not considering the trend. So you have two different techniques that we saw. Momentum was considering averages, and it was trying to use averages to smooth things out, but then that was ignoring the actual variation. RMS prop was considering the actual variation, but it was ignoring the average. So it was ignoring the trend. The obvious next thing to do, let's combine the two. And so when you combine the two, here's what we will do. You're going to maintain a running average of the derivative, as you do in the case of momentum. You're going to maintain a running average of the variance, of not the variance, the second moment. And now the update is going to use, this is the same as the update rule you had for RMS prop, except now instead of using just the local derivative, you're using the expected, the average derivative over the running average of the derivative out here. So this is Adam, which combines the best features of momentum and RMS prop. There's this extra equation in the middle, which I'm going to kind of skip. I'm going to, let's explain this. So this thing is an engineering kind of hack. Look at the slides, I'm out of time, so I won't actually spend time on that, right? So we've looked at these techniques, and there are very many variants of the same theme, which sort of follow the same theme as Adam, where you combine both the first moment and the second moment of the derivatives in the history to come up with the next update. Now, last couple of minutes, there are some nice visualizations that we have that I got from Alex Radford's webpage. And,
Professor, sorry to interrupt. Do you still want to do the last poll?
Yeah, no, I don't, because we don't have time for it, right?
Okay, okay.
So Alex Radford came up with some really nice visualization of how the different optimizers work. This doesn't show Adam, but AdaGrad and AdaDelta are kind of similar to Adam. This is Beal's function. This is the optimum, and all of the estimates start from the same location, which is out here. And you can see that SGD, which is the red line, always follows the local gradient, ignoring the long-term trend. And the local gradients don't clearly point to the optimum. So it sort of gets there very slowly. Now, RMS prop smooths out the variations. So it sort of follows the same trend as SGD, but gets there much faster. But it doesn't take advantage of long-term average trends. Momentum and Nesterov, they only consider the averages, but not the total variation. So in the beginning, they kind of stupidly wander off to these places. But once they find the path towards the optimum, they get there pretty quickly, as you can see. Okay. And AdaGrad and AdaDelta, the blue and fawn colored curves, they give you some kind of a median of the two. And so they are faster than SGD, they're even faster than RMS prop. But when the momentum methods actually get the solution, they converge much faster than these guys. The problem with these fellows is their tendency to wander. So here's a nicer function which explains things very nicely. This is the so-called long valley, and it's saddle-shaped. SGD finds the derivatives, and the derivative is 0 over here. So SGD is going to eventually just sit down out here and not do anything. RMS prop is going to cancel out variations in this direction. So it slowly comes down here. But then once it gets to the region of uniform slope, all steps are the same length. So it sort of takes its time converging, right? Now, momentum and Nesterov, they sort of wander around. But once they figure out that this is the wrong direction, they sort of speed down, and you can see what's happening. And AdaDelta avoids the initial oscillation, but then also zooms down the valley. So these visualizations are really nice. And this last one actually shows you the best result, gives you the best illustration. It's a complex looking curve, and you can see how SGD is basically taking its time. RMS prop is slow, right? But the momentum methods, once they figure things out, they're really fast. They can end up spending time just figuring things out. Whereas some things like Adam and AdaGrad are going to do something which is in between the two. And so in the end, they won't be as fast as momentum, but their behavior is much more consistent.
Professor, is there any benefit, like downside that momentum explores a little bit more? Does it have an opportunity to find a better local minimum than?
It does, but moment. So yes and no, right? It also runs the risk of just spending its time wandering around these stupid places, as you can see. In every case, once it finds the path to the optimum, it's going to be faster than the other methods. Nesterov's is more so than momentum, right? Nesterov's is NAG is Nesterov's accelerated gradient. It's optimal when you actually have a clear path to the minimum. But you have to take a chance on it finding the right position, whereas these other guys will actually get to a local minimum much faster. I mean, much more consistently. In all cases, we are only speaking of a local minimum. We can't speak about the global minimum. Although my guess is that if you wanted to get a better shot at finding the global minimum, then the initial explorations of these momentum methods might help. Did I answer your question? Right. So I'll stop here. I won't read this last slide. I went way over. My apologies. We'll have the questions thread up on Piazza, so please post your questions there. Thank you, guys. Stop the recording, boys.